Hello everyone, I'm Stuart Harper. I'm a postdoc at the University of Manchester, and I'm going to be talking to you about the Comap Galactic Plane Survey. And the way we're going to do this talk is we're actually going to split it up a little bit. So we've got me, I'm going to be talking about the overview of the survey and the data analysis at the beginning. And then our PhD student, Thomas Rennie, is going to actually be taking over the second half. He's going to just introduce you to some of the science that we've already been doing with this survey. So anyway, to begin. Okay, so this is the Comap collaboration. This Comap collaboration, we are a collaboration of about 10 institutions. I say about 10, these collaborations, when they're old, they fluctuate slightly, so it just changed, but this is the main set of institutions. And here we are back in 2018, standing in front of the Comap telescope, which is a 10-meter dish set out in the Owens Valley Radio Observatory, which is in California. And the Comap experiment, okay, I really should have said that down. The Comap experiment is primarily actually is a cosmology experiment. It's not what I'm going to be talking about today, but the main science is to do CO intensity mapping at redshifts of about 3. So this is the carbon monoxide 2-to-1 transition. And the aim is to basically try and detect CO, for the integrated CO emission from galaxies around redshift 3 and measure star formation rates, star formation histories. And maybe in the future, the plan is in the future that this will also expand from what is initially going to be mostly just a detection experiment of CO at these redshifts to a experiment where, like other intensity mapping experiments, like the H1 intensity mapping experiments, where we can actually map out the matter density field at these redshifts in a large volume. So the technical points though, the survey or the instrument is that we are a 19-feed focal plane array. We have 26 to 34 gigahertz frequency range, which is split up into 2 megahertz bands. So we have quite a lot of reasonable spectral resolution. We're not quite a spectroscopic instrument, but we have a lot of spectrum to play around with to basically handle systematics mostly. And we're at 4.5 arc minutes resolution, and we are intensely only. So yeah, we should point out, we're not going to be helping these QU B mode detections experiments, but we can help in intensity, and we think that as a map or as a data set will be really useful for Cosmoglobe. So this is the plan as we have it at the moment. The target, we want to basically map out all of the observable northern hemisphere part of the galactic plane, which is about 20 degrees to 200 degrees in longitude. There's a bit of wiggle room there, depending on how we do the observing, but that's more or less what it is. What you can see here is basically a map from, in the gray scale, is a map from the Planck 30 gigahertz survey, showing, and the red box is basically where we're trying to observe, or where we will observe by hopefully May next year. And the little color map there is the Comap survey as it stands at the moment, which is most covering between 20 and 42 degrees, with small excursions there, as you can see, to higher latitudes than the rest of the survey to cover interesting features. In that case, that was W40. So what is the most important thing about the Comap survey? Well, in terms of how the Galactic Plane Survey could contribute to Cosmoglobe. And I think the main thing is it fills a gap in frequency space at a resolution that no other survey is doing. Basically, we are observing at 30 gigahertz nominally at a resolution of 4.5 arc minutes, which means we match the HFI, right? So we are basically the same resolution at HFI, but instead of having to match that at radio or microwave frequencies with the LFI, which is half a degree resolution, you get 10 times better, roughly, resolution using Comap. So you can do that component separation in the very complex region of the plane where there are lots of components, to a much more accurate degree. You know, you can really start pulling out the individual free from the spinning dust from the synchrotron in the galactic plane by using these high resolutions and decomposing things in much more detail. We're also well placed for in terms of doing galactic science, as well as being matched to the resolution of the HFI. We are also well matched to a lot of other surveys. So at the lower frequency end, this is a table of all the surveys at the lower frequencies that we sort of match in terms of resolution. And the top half of this table, so we've got all things from VLA surveys, Effelsberg surveys, Parkes 5 gigahertz surveys, and there's also a few interferometric surveys, such as the MI and the VSA galactic plane survey. But the key thing to say, actually, I did forget this on the previous slide, is the VSA survey. So there is a VSA survey at 30 gigahertz. This is the only one that exists nominally near our frequency range, which is it was with a very small array and only covers a very small chunk of frequency galactic longitude space, but also loses a lot of the scales. So comparing that with Planck isn't ideal because you've only really got the beam scale, which was about 10 minutes, whereas we are preserving hopefully most of the scales in the sky. So you can really look for diffuse emission. In terms of the main science goal, we're mainly looking for anomalous microwave emission. Like that was the science case for this, the main science case. So if you don't know what anomalous microwave emission is, this is the dust correlated microwave emission that was detected in the COBE virus observations correlating with IRAS back in the 90s. And since then we've detected it everywhere, high latitude cirrus clouds to individual molecular clouds like the Rowoff-Eucus and Perseus molecular clouds. So, and lots of individual objects. But to date, actually surveying at these high resolutions where we can make out individual H2 clouds and star formation regions and supernova remnants all along the galactic plane, this hasn't really been done for anomalous microwave emission. So we really hope that we will be able to nail down some of the key questions. One of which is, of course, knowing whether or not anomalous microwave emission even really exists en masse, because there is the possibility, of course, that, and some people believe this, that it's just optically thick H2, right? And we can combine with these lower frequency surveys, such as the AMI 15 gigahertz survey, to really pull out this information, right? We can really distinguish whether or not it would be optically thick H2 regions or if it is anomalous microwave emission. And this will lead, hopefully, to better understandings of the mechanisms, which hopefully will lead to better models, which we can then use in Cosmoglobe. But also look for things like fractional content of AME, how it links to star formation, how it links to different environments within the galaxy and dust creation, and all these other sort of interesting science and astrophysical questions. There are other interesting science cases that we can look for as well. So I've already mentioned that there's a link between anomalous microwave emission and ultra compact H2 regions, but we can just look for ultra compact H2 regions in and of themselves. How they, although we don't have the resolution to distinguish individual ones, we can look for their integrated emission and how they contribute to the total energy budget of the galaxy, basically. We can also do, there's also lots of supernova remnants still at 30 gigahertz that we can look at. Primarily, these are ones where they are being re-energized in some way. So you have mostly pulsar wind nebulas on the smaller scales, but you also have Fermi accelerated or shocked shells from expanding supernovas that are expanding into the ISM. We also have questions on, for example, the flattening of the thermal dust spectrum at low frequencies, and we can look for infrared dark clouds that show evidence of this flattening at low frequencies. And of course, we also have spectroscopic information. So in principle, we could also link this into things like radio recombination line, or do our own internal radio recombination line survey, although that might be further off into the future. And then, of course, yeah, how does this link to Cosmoglobe? I've sort of said these points before, but the main thing is it's just going to replace the Planck LFI 30 gigahertz point along the galactic plane. And that will give us hopefully much better constraints on some of the parameters that we want to measure at that point, which would be, of course, the anomalous microwave emission amplitude, the amplitude of the free emission, and to some extent also the synchrotron emission, but it's mostly AME and free along the galactic plane that would be constraining. So I'm going to look a little bit more in detail now at the nitty-gritty of our data analysis, or some of the data in general, and what problems we face. So one of the main challenges, if for a ground-based observatory observing at 30 gigahertz, is that we have to contend with the atmosphere, and more specifically, a specific content of the atmosphere, which is water, the H2O in the atmosphere. The precipitable water vapor specifically is the most difficult thing to handle, which is basically, if you look on this plot on the right, this is showing the spectrum between 10 and 100 gigahertz of the Earth's atmosphere for different water content. So you've got the light blue line, which is where the relative humidity in the precipitable water vapor is 0. And then I've just basically increased the water content for different relative humidities. And you can see that, the relative humidity can change the brightness temperature, the effective brightness temperature of the atmosphere quite significantly by factors of 2 to 10 very quickly. And of course, if you, I've been doing a lot of gardening lately, so I've been looking at the relative humidity of my garden. I know that it can change quite dramatically. And of course, that can change very quickly over the course of a day. And that basically generates a correlated noise within your radiometer. And that is also correlated across frequency. So it's a continuum source. We're trying to measure a continuum emission, like free emission and spinning dust emission. These are continuum emissions as well. So decoupling those from each other is very difficult. There is also problems, sort of the total atmosphere brightness, the line of sight, the integrated brightness of the atmosphere, which is correlated with the elevation, which we can see in this bottom left plot, basically causes, because of our scanning strategy, we do these figures of 8 on the sky in azimuth and elevation. For crossing angle, that's to constrain the crossing angles of the data, so we can map the data and remove the 1/f noise better, which I'll talk about later. But you can see that it causes these ripples in the data to do with the atmosphere, but this is very easily modeled. The main problem is the fluctuations in the turbulence, basically, in the atmosphere. To give you an example of what it looks like after we do some post-processing and filtering and cleaning, etc. Clean data is what it looks like on this is the left. This is where it's good weather, it's all stable, it's clear skies, there's no clouds, etc. And you can see that, in general, we get very white noise. There is some 1/f noise. This is what this power spectrum plot is showing on the bottom left here. But it's, hopefully you can immediately see that it's much better than this plot on the right, where we have basically very turbulent weather systems going over, and some clouds actually on this particular day, which are going through the data, and they just completely ruin everything. And you have very large scale fluctuations that are very hard to remove in map making and in pre-processing. Also, the main problem is that if you have good data, these are correlation matrices in the bottom left here. So if you have good data, the correlations between feeds is actually very low. So we are, again, 19 feeds array. So if you correlate the data between those, if they are saying the same things, we should have a high correlation, but in general, we don't, because they don't share beams on the sky. But if the atmosphere is very turbulent, you can see that here on the right, these plots are showing the correlation is very high between feeds. Basically, they are seeing the same turbulent atmosphere, because in the near field, up to a few a couple of kilometers, you know, you are seeing the same water content between each feed, and they are correlating with each other, and so they see the same fluctuations basically. This plot is also showing the in-band. So do you see this? If you can look at this diagonal, you can see that there is there are high correlations within feeds. So this is the frequency correlations. This is another challenge that we actually have to overcome with the continuum data, is how we decorrelate the frequency data. And the last sort of challenge, the main challenge which we have, is of course, because we're on the ground, we pick up the ground around the observatory. We are in a valley in Owens Valley, as the name suggests. So we have mountains on both sides, and yeah, we basically measure those in the side lobes of the instrument. So that has to be handled too. I'm running a bit low on time, so I'll skip that. This is the calibration. So I'll just say, well, we calibrate the data using a microwave absorber. What we basically just cover the focal plane array. We calibrate to basically the difference between the cold sky and the vane's ambient 300 Kelvin temperature. And then that gives us sort of the long-term gain stability. But then we match that to a astronomical calibration, where basically we measure 2D Gaussians on sources, specifically Tau A and Cas A, two very bright supernova remnants, and Jupiter, which is obviously a planet, which is very well modeled at microwave frequencies and makes an excellent calibrator at 30 gigahertz. So these are just basically the plots over time versus our models for the different calibrators, for two calibrators. And you can see that we do match reasonably well the calibrators once we calibrate the data. We actually get to within a few percent. So it's 3 to 5%, depending on the band exactly, over time in terms of calibration stability. And then in terms of frequency calibration, we get a little bit better. We get to 2 to 3% once we calibrate to Cas A or Tau A. These two plots basically on the left and right are just showing the comparison between the fluxes that are measured, which are the boxes, to the model, which is the dotted line here. And we are using Cas A to calibrate Tau A, and Tau A to calibrate Cas A on the right. Basically, we're just doing cross calibration here, just to cross-validate everything's working. And yeah, so we get within a few percent. So the calibration is pretty good. The main thing, though, to bear in mind is that we're not a perfect instrument as well, like the Planck. In terms of its beam, we don't have 98% beam efficiencies. We're more of a normal telescope, so we do have significant side lobes, inner side lobes. So we are trying to quantify those. We've done these mostly by stacking observations of Jupiter, which is this plot on the left. You can't quite see the side lobe in this plot, but once you do a radial profile, which is what you can see on the right here, and compare it to our beam model, which was generated in GRASP, which is the black dashed line, you can see that we basically can track and recreate the expected inner side lobes out to at least the second side lobe here, but potentially you could argue that we were also detecting the third side lobe here at low sensitivity. And from my understanding of Cosmoglobe, it's going to be very important that we provide these beam models, and then this is how basically the different scales have different calibration factors, which we can also provide. And then the final slide for my section, which I hopefully not taken all of Thomas's time, is just to say about the data volume. So in terms of the reduced data, the calibrated data, which I was showing earlier, the current size of that is about 1 terabyte for about 150 hours, but the final data set will be about 10 terabytes in terms of the time ordered data. But if you really want to go back to the very raw data, well, the final data set is going to be about 150 terabytes. So things start becoming unmanageable very quickly just because of the spectroscopic nature. of the data set. We could also reduce this down a lot more by a factor of 8 if we don't include any spectroscopic information and just integrate our full band, 8 gigahertz band to a single band, then you're working with 1 terabyte of data. So it can be small, it can be large. It depends how much the Cosmoglobe guys you basically want to handle this if you do want the TOD data in the future. And from there, yeah, I'm just going to hand over to Thomas.
Fantastic. So hi, I'm Thomas. I'm a PhD student at the University of Manchester, working with the COMAP Galactic Plane Survey, and particularly digging into the scientific analysis of it. So if we can go to the first slide. So this is the COMAP Galactic Plane Survey as it stands today. So stretching between plus and minus 2 degrees galactic latitude, and then longitudes between 20 and 43 degrees. Just to fill in a couple of details on that. So if we can go to the next slide. So the main bright regions along the galactic plane are star-forming regions. A lot of the emissions heavily dominated by H2. So I've labelled those on there for you. A lot of them collide with the West-Hout regions, first detected in the optical. I've also highlighted a couple of other sources, but just to pick out some of the more interesting of them. The source in the cutout right at the bottom, RCW175. We've talked quite a bit about AME, and it's come up yesterday as well as Stuart mentioning it earlier on in this talk. But RCW175 is a confirmed AME source, but previous analyses have been done at higher resolutions, at higher beam widths. So with our finer resolution, we're able to begin to really differentiate the 2 H2 regions that make up that source. And so hopefully sort of localize that AME a lot more, which comes down to, as Stuart says, AME isn't really well defined at 4.5 arc minutes along the galactic plane. So in addition to that, we have supernova remnants such as KES69 and G21.5 minus 0.9, which I've labeled on the right-hand side. G21.5 is a pulsar wind nebula. And then KES69 is a shell-type supernova remnant. But in addition to those sort of sources, we also see diffuse, a lot more diffuse emission, so such as the source I've highlighted on the left-hand side at about 38 degrees galactic longitude. And there we think those are synchrotron filaments that we're seeing in the COMAP dataset. So you can see this is a really rich dataset, and it's very interesting to sort of begin to dig into. Go to the next slide. Within COMAP, we've talked about having this 8 gigahertz bandwidth to play with. And so at the moment, what we're favoring for our galactic science is to split that up into 8 1 gigahertz bands. And then we can do some internal spectroscopy just within the data provided by COMAP. And so you can see for W43, I've produced all 8 bands on the left-hand side. And while the differences aren't necessarily as pronounced there, on the right-hand side, you'll see a difference map between the 26 to 27 gigahertz band, and then the higher frequency 33 to 34 gigahertz band. So we do see some differences between the two, and they can help us to identify those regions we want to dig into. Yep. Then on the next slide, we've got, so obviously the natural survey to compare with, particularly within the context of CMB, is the Planck LFI 30 gigahertz map. So in the top left-hand corner, you can see, again, another view of W43, that big star-forming region in the middle of our current survey, with COMAP on the left-hand side in its native resolution, and then the Planck 30 gigahertz on the right-hand side in its native resolution. You can see quite a difference in the resolution we're able to achieve. So in order to do a more sort of robust analysis between the two, I've gone and smoothed the COMAP data to the resolution of Planck. And you can see in the bottom left-hand corner, we've got the smoothed COMAP map with Planck 30 gigahertz contours around it. And you can see that we have relatively good agreement between the two, especially as seen by the residuals in the bottom right-hand corner. Yep. Going further and comparing with other surveys, so starting with low frequency, so comparing with the Parkes 5 gigahertz continuum survey, which is mostly seeing free. So we'd expect that to sort of track H2 regions and that kind of thing. We can see that there is some really good correlation there, particularly in point sources. So it does back up that we are seeing a lot of H2. However, I've also boxed in 3 regions where we do see a really good peak with Comap, but it's not necessarily traced as well in the Parkes 5 gigahertz, which is, again, where we'd begin to look into as regions of interest potentially for AME. On the next slide, we then compare to Planck HF5353, so looking more at thermal dust. And the take-home message from this side is more that this appears to be sort of more diffuse at the moment. And it appears that we're sort of tracking the diffuse background emission more. But again, we really need to go into this in a little more detail, as will be done for the first paper coming out at the end of this year. On the next slide, we can again go into that diffuse emission a little bit more. So Westerhout 44 is a big pulsar wind nebula, and what you see as the emission is the shell, which as it meets the ISM. You have Fermi acceleration, and so on the near side, so in the bottom left-hand corner, you can see that that's much brighter, and that's simply due to that effect. Taking a cut along the dashed white line, just within the Comap bands, we get to the cuts as seen in the top right-hand corner plot. And again, just to emphasize, those are just the Comap bands, so from the 26.5 through to the 33.5. And then from those, we can calculate a spectral index. And we're beginning to see that there is a split in that spectral index between those two main parts of that nebula. So you can see even just within the Comap data set, we do have a lot that we can begin to dig into and offer the collaboration in that respect. Moving on to the next slide, we can see more on the Westerhout 43 region, which I just wanted to mention really because it's going to be the subject of the first paper, the first galactic science paper for Comap. And within that, we do have a lot of sources that we can really dig into. So on the left, you can see a smooth bin map of YSOs. In the middle, that's Cornish data, so a simulation of UCH2. Then on the right side, we've got the top 10% of brightest YSOs, H2 regions, and supernova remnants within the W43 region. So again, it's quite an interesting and busy region for that. On the next slide, this just explains our SED extraction pipeline, which we're using to extract out point sources at the moment in order to sort of really do a more robust analysis on those and begin to put together a catalogue for the first paper. And then on the next slide, you can see a couple of example SEDs. So the two on the left-hand side, so the G37.32 and then the G31.05. Those are both H2 regions that are around, that are within the area of we've got highlighted for the first paper. And then on the right-hand side, 3C391 is a supernova remnant, which is just on the side of W43, and you can see that the Comap points in the bottom right-hand corner, and actually in the small cutout as well. We're able to sort of track that dropping frequency even within the Comap data as well. And then finally, just moving on to sort of take-home messages from this talk. So Comap is a 30 gigahertz 4 arc-minute survey of the galactic plane as observable from the Northern Hemisphere. Our current coverage is between 20 and 43 degrees galactic longitude for between plus and minus 2 degrees galactic latitude, but we will put in extra fields for other points of interest as we move up through that range. Our current intention is to complete the survey by May 2022, assuming the current rate of progress. So that would reach 200 degrees galactic longitude, with the first science paper due for release at the end of this year. The release of the maps will then come shortly after the initial science papers. We've not got a current plan for the release of the time-ordered data, but we can look at making that available upon request. But that would be around the order of 1 terabyte for the full 8 bands data sets. And then the main challenges that we've gone through with this, obviously being atmospheric fluctuations, frequency, noise correlations, and ground pickup. But hopefully we're getting past all of that okay at the moment, touch wood. Yeah, any questions?